Okay, we're back at it again. Today we're talking about condensation reactions. So when we first started talking about enolates, we said that we were going to use them to attack a bunch of different nucleophiles. Yesterday, or in the previous lecture, we saw the enolates attack halides, and we did alpha substitution. Today we're going to have enolates attack carbonyls. And so we're going to use the enolate as our nucleophile. So we'll form that by deprotonation of an alpha proton. And then what we'll do is we will attack a carbonyl, kick the electrons up onto the oxygen, and do an addition reaction. Now, this is one of the most important reactions biologically. This is how we make fats and break them down. It's used in glycolysis. And so it's a very applicable reaction to biochemistry. So if we actually just take a aldehyde and mix it with sodium hydroxide, sorry about that, technical difficulties. So if we take a aldehyde and we mix it with sodium hydroxide, and since that's a solid, it needs to be dissolved in a little bit of water. What we see is two molecules connecting to each other, forming an aldehyde and an alcohol. And since we have an aldehyde and an alcohol, this is known as the aldol reaction, coming from an aldehyde and an alcohol. Notice here we have the alpha carbon to this carbonyl. That's very important to be able to recognize. When you see a carbonyl, look for the alpha carbon, and then we know that this is the bond that we made. So under basic conditions, what we can do is take a base. Remember, sodium hydroxide is not a very good base to get 100% deprotonation of the enolate. So we do set up an equilibrium between the aldehyde and the enolate. But we do get a little bit of this enolate, which is enough that it can go and attack another aldehyde. Remember, aldehydes are more reactive than ketones. So this is a really good reaction. So it will go and attack that carbonyl, kicking the electrons up onto the oxygen. And again, what we've done is we've made this bond right here. There's the alpha carbon that we deprotonated. We've made a new bond. We've added to the carbonyl. And then we simply have to protonate with water. And that will give us our aldol product. Now, this doesn't have to occur between an aldehyde. It can occur between ketones, but they're still known as the aldol reaction. And the key for the aldol reaction is we always get a beta hydroxy carbonyl. So anytime you see a beta hydroxy carbonyl, that came from an aldol reaction. So, as I mentioned, it's a fairly good reaction. Even though the sodium hydroxide only makes a very small amount of enolate, we can produce quite a bit of product. And so again, if we want to see the bond that we made, there's our alpha carbon. We disconnect between the alpha carbon and the alcohol there, and we get this in 75%. So for simple aldehydes and many ketones, it favors the products, but not for all. So in some cases with ketones, such as this cyclohexanone, we actually do get product, but it actually favors the reactants. And that has to do with sterics as well as ketones being less reactive than aldehydes. But again, if you saw this on the test, you'd want to list this as the product because that is the major product of the reaction. And again, we can identify the alpha carbon. So you find the carbonyl, look at the position next to it, that's the alpha carbon. And the bond that you made is between that alpha carbon and where the oxygen is attached. And these are called aldol additions. So in some cases, if you force this reaction with a little bit of heat, the reaction continues and you go from this aldol addition product. Again, you can see the alpha carbon here. You can see the bond that we formed right there. But if I add some heat, I get a new product. And that's off to the right here, the alpha beta unsaturated carbonyl. So we saw how to make these yesterday by putting a bromine at the alpha position and then doing a E2 elimination. But we can actually go straight from an aldol reaction to this alpha beta unsaturated carbonyl. And the key requirement for that is heat. So watch for test questions that say, draw the product of the aldol addition. That would be this product right there. That's the aldol addition. And then watch for questions that say, draw the aldol condensation. The condensation is when you combine molecules and you get rid of a small molecule such as water. So this is the condensation product right there. Now you don't always need heat. For us, that will be the key that you want the aldol condensation. But in some cases, and if you're going to be doing a lab, you would actually see this. So in this case here, we're going to take this ketone and we will deprotonate at this alpha position right here. And if it reacted with itself, again, here's the alpha carbon, there's the bond that we made, and you'd get this beta hydroxy carbonyl compound. But notice it's in brackets. You don't isolate this. It actually rapidly undergoes the dehydration to get rid of water to give you the alpha beta unsaturated carbonyl. You get that double bond. And I'll give you a second to try to come up with a reason of why this compound right here specifically would actually go straight to the condensation product, where this one here requires heat. This one here, no heat. It just goes straight to the alpha beta unsaturated carbonyl. And if you look, the answer is in the difference. What we've got here is a very conjugated system. We can go from the aromatic ring through that double bond up to the carbonyl. And so due to that conjugation, this molecule ends up being very stable. So in this case here, you get a condensation reaction producing a extended conjugated system, and that doesn't require heat. Again, for me, anytime I want the condensation product, I'll indicate heat, or the question will say, draw the condensation product from this reaction. But it is important to know that in some cases, these will readily undergo the condensation reaction, and that's when you get molecules that end up having this extended conjugation. What's interesting about these molecules is they also tend to be colored due to that conjugation. Okay, so let's go through the complete aldol addition and condensation product. So how does that work? And so first of all, we need to deprotonate and form our enolate. Again, not a very good base, but we are going to park those electrons on that alpha position there. Again, I'll stress that you can draw it in the alternative resonance form with the O- up there. Organic chemists, just being lazy, tend to park those electrons on that carbon, and that is where the nucleophile is. If you choose to draw the major contributor, you can still do this reaction easy. You just drop the electrons from the oxygen down into that double bond, and they go out and attack the carbonyl and kick electrons up onto the oxygen. And that would lead us to the exact same product. And then finally, you work it up with a little bit of water and you get your beta. Again, there's the alpha position, there's the bond that we formed, there's the beta position, the beta hydroxycarbonyl. So how we get the elimination reaction is we still have an alpha proton here. And so what we're going to do is deprotonate that alpha proton. We're going to park those electrons on that alpha position, and then they collapse in and kick out that OH. And that's how we get the double bond there. So the question comes up, can I do that all in just one step? Can't I just have that come in and do like an E2 elimination? So I'll draw that in blue arrows. Why can't I just save myself a step, pull those H's off, come in here and kick off the OH? Well, that's bad because it's not an E2. It's what's known as an E1CB. And so the reaction actually occurs through a different mechanism. So I'll erase some of this over here. And this is where parking those electrons on that alpha carbon is somewhat deficient in explaining this. So I'll redraw the molecule over here. And again, we'll accept how it's drawn in the book, but a little bit better way to look at it is you pull off that alpha carbon and you push those electrons up onto that oxygen. You've got this double bond here. And now what you do is collapse those electrons down, pop over, and they'll kick off that OH minus. And so in the end, we end up with the exact same product, the alpha beta unsaturated carbonyl, but not through an E2 reaction. Again, if you just happen to show the electrons coming in here and then you come over and kick that out, that would be an E2 mechanism, which this is not. So you've got two ways to show it, over in the blue on the left, or shown like it is in your book, where you have to park those electrons here on the carbon, draw that structure, and then collapse them out. And so the question is, I didn't think OH was a very good leaving group, so why is it leaving? And again, the answer is in the difference in the product here. So if you look, by kicking out the OH, you end up with a conjugated carbonyl. So OH minus is a poor leaving group, but in this case it does leave, and we end up with these alpha beta unsaturated carbonyls. So we're unsaturated between the alpha and beta position. So again, what we have here is the aldol addition or the aldol product. That comes from just adding one enolate to the carbonyl. So that comes in and attacks, and then it gets protonated, and that gives us the aldol addition. We can get the aldol condensation when we add a little bit of heat. And when we add a little bit of heat, that gives us the dehydration here, which leads to a conjugated system. So as I mentioned earlier, in some cases, it's not possible to isolate the aldol addition product. So again, what you'll notice in this one is we have an aromatic ketone that leads to an extended conjugated system. And so in this case, it's not possible to isolate the aldol addition product. Again, for me, the hint that you'll get that is I would always put heat here So NaOH and heat will lead to the aldol condensation product. So there's a quick and dirty method to get the aldol condensation product. And we're having technical difficulties again. And we're back. So there is a quick and dirty method to actually identify the aldol condensation product. So if I just took acetone, what you can do is you line up that carbonyl with the alpha carbon of the other carbonyl. And you can almost think like this is a spaceship docking. And so what happens is that spaceship will dock into that alpha carbon position, open up the airlock, which removes that oxygen there. And you now have the product from the alpha beta, or the product of the alpha beta unsaturated carbonyl. So this is a way to be able to identify the aldol condensation. So you can see another example that your book shows of how to connect those. But this is also useful if you see an alpha beta unsaturated carbonyl, of how to disconnect them and identify what carbonyls they came from. And so I'm always a fan of not rearranging the atoms, drawing it as similar to the picture as possible, which that's a very bad example. So we'll try it again. So you try to draw all the atoms in as close to position as the problem gives you. And then what I'm going to do is just disconnect from that alpha position, and that shows me how, or what two carbonyls gave me that alpha beta unsaturated carbonyl. So we've got a problem here, predict the products. So we'll give you a second. In one of them, we're doing it at 10 degrees Celsius, and in another at 100 degrees Celsius. So in both of these cases, we're going to deprotonate at the alpha carbonyl, and what we're going to do is a aldol addition, and one of these will be an aldol condensation. So that would come over and attack the carbonyl. If you remember earlier, we talked about this reaction not giving a lot of product, but the major product that we would get is the aldol addition when we did it in 10 degrees Celsius, and the aldol condensation when we did it under 100 degrees Celsius. So these would be the products that we would expect. And again, you can see that we just docked one carbonyl at the alpha position, forming a double bond there. So we can make this a little bit more complex by taking two different compounds with two different types of alpha protons. So in this case, we're just going to take two different aldehydes, propanal and ethanal, and you can see they both have different alpha protons there. And if we look, we can see that we get a multitude of products. And so those products come from this enolate here reacting with itself, which what we would call a self-aldol reaction. This enolate here reacting with itself in a self-aldol addition. This here, what we would call a cross-aldol reaction. So the enolate on the blue molecule reacting with the red, and then the red reacting with the blue. So we actually get 4 products. And that's kind of a lie, because we actually get a lot more products than that, because we actually make stereocenters there. So we'd actually get a mixture of R and S there. We would get a mixture of R and S here, a mixture of, and a mixture of R and S there. So it actually get 4 different compounds out of there: RR, RS, SR, and SS. And that would be the same here, and then we'd get a mixture of R and S there. So if I'm counting right, that's 12 different products out of this reaction if we just mixed these two. So this is a very poor way to run reactions. So must the 2 molecules be the same? And the answer is no. They don't have to be the same molecule, but if we want to do these crossed aldol reactions, we have to have some way to control them. Otherwise, it's not synthetically useful and we get a lot of different products. So what we refer to as practical crossed aldol reactions, these are reactions that can actually be done. And there's a couple different tricks that we can play. And one of the tricks that we can play is that we can react 2 different molecules, but only one of them has alpha protons. So in this case here, we got propanol that has alpha protons and formaldehyde. So we can actually do a crossed aldol reaction here and get the aldol product, but we don't have to really worry about the condensation, or sorry, not the condensation. We don't have to worry about self-condensation here. And how we do that is we have lots of this in solution with the base. And that's just sitting around, and nothing's going to happen between the formaldehyde and the base because there's no alpha protons. And then what we're going to do is we're going to drip in the compound that has the alpha protons. And as we drip it in, it's going to make a small amount of enolate. And this is going to be in low concentration compared to the formaldehyde. And so this is going to be in high concentration. And so what ends up happening is we generate a small amount of this enolate, and it's most likely to react with the formaldehyde. In this case, the formaldehyde also is the most reactive carbonyl species there. And so we can control it by controlling the order of addition, and we can get our beta hydroxy carbonyl here. So here's another example down here. We take a compound that doesn't have alpha protons with a compound that does have alpha protons, and we can mix those 2 together. Again, this one here will tend to react here. If we control the order of addition, we have this sitting in solution, we drop this in. So this tends not to react with itself. It tends to react with the compound that's in higher concentration. Now in this case here, we'd tend not to get the beta hydroxy. Notice that heat's indicated. And so what we do is we actually get the alpha beta unsaturated carbonyl. And again, that's because we get an extended conjugated system here around the ring and into that, through that double bond and into that carbonyl. So one trick that we can play is we can make sure that only one of our compounds has alpha protons. Now there is another trick that we can play, and that is to use a reagent that forms 100% enolate. And so if you remember, the base that we used to form enolates is LDA, lithium diisopropyl amide. So it's just an N-, very strong, and what it does is it gives you quantitative or 100% deprotonation of whatever carbonyl you had in there. So in this case, we're starting with acetone, and we want to deprotonate it completely. Notice that that is an irreversible arrow, so we're not setting up an equilibrium here. And so in this case, we get 100% of that enolate, and then we add in our second carbonyl, the one that we want to add to. And it will react, we protonate it, and we've got our beta hydroxy carbonyl, and we don't have all the other products to worry about. We are going to get a mixture of R and S here, but that's 2 products versus 12. So the two options we have so far is having a reaction where only one of the species has alpha protons, or we use LDA to form 100% of our enolate. And then once that's formed, adding in the acceptor or the electrophile, and then we can control who reacts with who. And it's not a free-for-all between a bunch of different compounds with alpha protons. So the key is the deprotonated enolate will sit in solution as the nucleophile. So we deprotonate it. You do this at cold temperatures and it just sits around. It's all deprotonated. It's not going to react with another molecule. And the reason for that is everyone in solution is in the form of an enolate. I'll draw that over here to the left. And since everyone's in the enolate, there is no free carbonyl to attack. Again, we get 100% enolate formation. And then the next step is once that's done, we just let it stir for a little while, and then we finally add in our acceptor. So in this case, we're going to add butanal, and we can control who reacts with who. So essentially, we're selecting who our enolate is, and then it attacks the carbonyl. And so we can do crossed or mixed aldol. We just have to think about the order of operations and who we want to attack who. Okay, we can even make it more exciting than crossed aldol, and we can do intramolecular aldol. So in this case here, we tend to do aldol condensations, and since they're intramolecular, we're going to be forming rings. And the key to understand how these works is to be able to identify the alpha carbons in our compound. If you notice here, we've actually got 4 different alpha carbons. Since this molecule is symmetrical, we really only have 2 that we need to worry about. So if we look at this molecule here, we've got alpha carbons here. In fact, I will color these different. We'll call these the blue alpha carbons. And then we have the red alpha carbons. If I pull off the blue alpha carbons, alpha hydrogens off that carbon there, and it attacked here, what we would form is a 1, 2, 3, 4, 5-membered ring. And so 5 and 6-membered rings we can easily form. If I pull off the red here, those hydrogens, and I count 1, 2, 3, we'd form a 3-membered ring, which isn't going to be very favorable. So we are going to pull off the protons that allow us to get 5 and 6-membered rings. And so in this case here, we would pull off these alpha protons. Those would form an enolate, and then they would go in and attack. And that ends up after we add some heat and we do a condensation reaction, we get a alpha beta unsaturated cyclohexanone, or sorry, cyclopentanone. So we get a 5-membered ring with a double bond. So we can actually form 6-membered rings. The key here is we would just need a few more carbons from that alpha carbon. Not really a few, 1. We would just need it so that when I pulled off those alpha carbons, that is now 6 carbons away from that carbonyl there. And that would react with a little bit of heat, and we would get an alpha beta unsaturated cyclohexenone. So again, we can figure this out by what's going to happen by identifying our nucleophilic site. Those are going to be alpha, always to a carbonyl. So I could possibly use this site over here, but if I counted, that would be 1, 2, 3. If I use this site over here and this image to the top right, and I counted, that would be 1, 2, 3, 4, 5. So let's look at this example down here, this 1,4-diketone. and look at our possibilities. Again, we're going to have two different alpha protons. I got these on the outside, I got these on the inside. So if I count from the red alpha protons to the carbonyl, that would give me a 5-membered ring. If I count from the blue alpha protons to the carbonyl, that would give me a 3-membered ring. So you can see that the red alpha protons would give you a 5-membered ring, and the blue alpha protons would give you a 3-membered ring, which is not going to be favorable. So we have a choice here. We can form a 5-membered ring or a 3-membered ring, and we're going to form the 5-membered ring because it has less angled strain. So here's just another example of it. So this is the same as the previous page. So I can come in and attack here and get a 5-membered ring. Again, with a little bit of heat, we end up with the alpha beta unsaturated carbonyl. If I took the inside protons here and removed them, formed an enolate, I would get a 3-membered ring, 2-strained. So that's not going to happen. So the greater the stability of the 5- and 6-membered ring causes them to be performed preferentially. So I can actually take down here in the bottom left a 1,6-diketone. And again, I have two different types of protons. I have those on the outside and those on the inside. If I count from the blue to the carbonyl, 1, 2, let's try that again. 1, 2, 3, 4, 5, 6, 7. So I could get a 7-membered ring. Or if I counted from these inside, that would be 1, 2, 3, 4, 5. And again, we prefer 5- and 6-membered rings. So the 7-membered ring is not formed, and so we would end up with a 5-membered ring. So if you start looking at this, you'll always get options between 3 or 5, or 4 and 6, or 5 and 7, or 6 and 8. And hopefully by now you can figure out which ones you choose. If you have an option between a 3 and a 5-membered ring, you choose the 5. If you have an option between a 4 and a 6, you choose the 6. If you have an option between a 5 and a 7, you choose the 5-membered ring. And if you have an option between a 6 and an 8, you would choose the 6-membered ring. Okay, we're going to stop there. That's enough to digest in one round. And I will post the Claisen condensation shortly.